All right, we have discussed divisibility a little bit. Now we're going to move on to the next section and talk about modular arithmetic, still kind of in some foundations related to number theory. So just think for a moment about seeing clock instead of on a 12-hour system. Maybe it's on a 7-hour system. Okay, so 1, 2, 3, up to etc. up to 7. So if it's at 4 now, what will it be at 24 hours, and what will it be in 31 hours? Okay, so again, you only have the numbers 1 through 7. Take some time and think about that. Pause the video and resume when you're ready. When we think about this clock, we think about an idea of congruence as well. It's not so congruent is the idea that it has the same value, but it doesn't necessarily have to have the same exact quantity associated to it. Okay, kind of like if you remember congruent from congruent triangles or whatever, you could have the angles be the same, but maybe the orientation of the triangles is different. Maybe it's in reverse order or something. Or you could have the same angle measure, or you could have congruent angles, but then maybe the side lengths of the rays that form the angle are of different lengths. Something like that. Okay. And so when we're talking about congruence in our context, we're typically saying that two numbers are going to be congruent if we're given this modulus m. Okay, so that's what m is called. M is called a modulus. And we say that this modulus would divide the difference of these two numbers. A minus b, b minus a, don't really care. And when we take their difference, and since it would divide, that means that there is a remainder of 0. Okay, so we're still incorporating our divisibility ideas. Okay, so then for our opening question, okay, you should have done something like this. Well, maybe you did, maybe you didn't. But if you imagined adding 24 to 4, that's 28. And then when you do 28 mod 7, or modulus with the modulus of 7, so we would perform the division algorithm and we would end up with 0. Okay, 28. 28 is perfect multiple of 7, as is 35. So we end up with 0, which technically in our system, so this our clock begins at 1 o'clock, so this would be at the 1 on our clock. Okay. Or 1 or 7, depending on your orientation of the clock. Okay, we're just going to deal with that. And actually, I think 7 would be the best, now that I think about that. Okay, so 7 on our clock. Okay, and then with this definition, of course, we have some propositions. Okay, so if we have two numbers that are congruent, A1 and A2, and another set B1 and B2 that are congruent, A1 and B, like A's and B's are not necessarily the same, then if we add or multiply them under this modulus, then we get the same thing. Okay, that's actually going to be a homework problem. Okay, so all I can say is use the definition for that one. All right, for B, I like this one a lot, and this gets at that idea of the GCD from an earlier video. But if we have the product as 1 for this modulus, then that's the same as saying that the GCD of A and this modulus, or equivalently B and this modulus, is 1. And then B in this, if we think of A and M here, B would be called the multiplicative inverse of A, or equivalently, if we switch it around, A would be the multiplicative inverse of B. Okay, so if we look at the proof for this part, I'm actually going to do the left to right first. Okay, so we're going to assume, so we're doing this direction first. Okay, so we let GCD of A and M be 1. Okay, so then what this means is that we can take A multiplied times U plus M times V is equal to 1. Okay, and then I'm going to kind of move the MV to the other side, the 1 to the other side. Okay, AU minus 1 is equal to negative M times V. Okay, and then so what this means is that, so then this gives that m divides AU minus 1, because we have that minus v. Okay, and so then all we have to do is we can say that, okay, so m divides AU minus 1, so then if I were to do all of this mod m, okay, we end up with AU minus 1 would be congruent to 0 mod m. Okay, you can always apply a modulus on either side. That is perfectly fine as long as it's done both sides. And then AU is equal to 1 mod m. And then so, oops, I should actually write that a little clearer. Let me redo that. AU. And then simply just take u to be b. Okay, that's the first direction. Now going the other direction, I wouldn't advise necessarily redoing your steps here, but we would say, suppose, so we would say there exists a b such that a b is congruent to 1 mod m. Okay, and then what this means by definition is that, okay, move the 1 to the other side, minus 1 is congruent to 0 mod m, and then this by definition means ab minus 1 is equal to c times m for c an integer. Okay, and then if you then rearrange this, so AB minus CM is equal to 1, and then this means that the GCD of A and M is 1. Okay, so it's similar, but I wouldn't, it's just a little wonky to go backwards. So this is the proof for that part. Okay, and then some other definitions in here. One common set of congruence classes that we look at are the ring of integers mod m, and so by definition this is what we kind of write it as, z mod mz, and this is just the integers 0 up through m minus 1. Okay, and then addition multiplication is normal, but we just take the result mod m. So I want you to pause the video and complete these tables and resume the video once you think you've completed the tables. Here are the completed tables. What you might notice when you are completing them is that it's a little bit like a game when you're completing them, because generally every row and column only has, at least in addition, has only one of each number, so it's a little bit like a Sudoku, except you can repeat numbers. And then in the multiplication, again, every row or column typically only has one of each number, the exception being 0. Okay. Now, in the multiplication table, if we're thinking about that last proposition that we proved in the GCD stuff, we might notice that 1 is its own multiplicative inverse. 2 and 3 are multiplicative inverses, because we get those appearing, right? So 3 times 2 was 6, and then mod 5 is 1, and then 4 is its own multiplicative inverse. So when note that all numbers don't necessarily need to have a multiplicative inverse in your ring that you're working with. And also one other caveat on the term ring is that it's an algebraic structure that we'll get to see later in the course. So don't worry if you don't know that terminology just yet. Okay, when numbers do have inverses, we call them units, and then the set, okay, so just notice that this is a set of all units. We call that Z mod MZ with a star set, with a star with it. So the set of so I guess Z mod MZ star, or Z mod, let's try that again. Z mod 5 Z star. This would be the set of 1, 2, 3, and 4. Okay, because 0 doesn't have a multiplicative inverse. Okay, and then Euler's phi function, we will use at various points in the course, just to make you aware of it, is defined as this. So just set of all numbers, or set of the set, or sorry, it's the size of the set of units. So in this case, when we're looking at phi of 5, it's going to be 4. Okay, because there were 4 numbers in our set, so that's all we have to do. Okay, so little overview of modular arithmetic: a theorem, or a proposition rather. You have to prove the other part, and then rings of integers.